Okay, today we are going to look at Lesson 65, Falling Body Problems, which this is a day you guys probably tend to like because it is physics involved with calculus. So you will have a lot of basic background knowledge on this lesson and just applying the calculus direction. So there's a little bit of recall here. So first of all, recall acceleration due to gravity is negative 9.8 meters per second squared. The negative, of course, is because the gravity is pulling in the downward direction, and so acceleration must be negative. The position function is given by the formula h of t equals negative 4.9 t squared plus v naught t plus h naught. I'm trying to remember what you guys say Dr. Austin calls this, because I think he does maybe v0 and h0. I don't remember exactly, but the v naught and h naught are your initial velocity and heights. Now, based on if h of t is that given function, then h prime of t, take the derivative with me, please. Derivative of negative 4.9 t squared is going to be negative 9.8 t plus the derivative of v naught t, which, remember, that velocity number is a number. This is just v naught. And the derivative of h naught is 0 because it's a constant. First derivative of height or position, remember, is your velocity. So this is also v of t, if you would. And then the second derivative of height, so the second derivative of position. So derivative of negative 9.8 t is negative 9.8. And derivative of velocity is just 0. And of course, if this is the second derivative, this is your acceleration formula. A few more reminders. The negative 4.9 t squared is there in order for acceleration to always turn out to be negative 9.8 meters per second squared. Now, a lot of what we do, and probably what you do in your science, works in meters per second squared. However, please recall that if they throw feet at you, the acceleration would be negative 32 feet per second squared, which means your position formula would have started off as negative 16 t squared instead of negative 4.9 t squared. As I already mentioned, the v sub 0, what I call v naught, is the velocity at time t equals 0, which is the initial velocity. If the object is thrown upward first, this will be positive. If the object is dropped, the velocity will be negative. And then what I call h naught, or h sub 0, is your initial height of the object, like if it was dropped from the top of a building. Obviously, if something starts at ground level, that initial height is 0. So let's look. We have 3 examples today. So let's look at example 1 and get going from there. An object is dropped from a height of 2,000 meters. Begin with the acceleration function and develop the position function. How far above the Earth will the object be 20 seconds later? So, let's go back to that first sentence and identify some given information. So in that first sentence, an object is dropped from a height of 2,000 meters. Well, 2,000 meters is my starting position. It's dropped from that height, and so this is my initial height, what I would call h naught. The other piece of information to notice is that an object is dropped from this height of 2,000 meters. It's not thrown, it's not thrust, pushed, anything like that. It is just dropped. And so if it's just dropped, what is that initial? That tells us my initial velocity. And the initial velocity is 0 because there's no extra push behind it. They ask us to begin with the acceleration function and develop the position function. Do you notice the word develop in there? Technically, when it says develop, you shouldn't just write down what you think or realize the equation is going to be. You should show the connection steps. And then in the end, we will have to find how far above the Earth the object will be 20 seconds later. So it says to begin with acceleration. So if we look at acceleration, notice the object was dropped, which means I'm going to have a negative acceleration. And acceleration, of course, is negative 9.8 because we are working in meters. So negative 9.8 for my acceleration. From there, in order to work to get to position, from acceleration we can go to velocity. And how do we find velocity given acceleration? Velocity is going to be the integral, because we're going backwards. So it's going to be the integral of negative 9.8 dt. I'm just going to work across my page here. The integral of negative 9.8 is going to be negative 9.8 t, and then of course it's an indefinite integral, so we're going to say plus c. What do we know that can help us find what c is? And the fact that we know our initial velocity, v of 0 is equal to 0, will help us to find our initial velocity. And so officially, if you fill this in, negative 9.8 t, officially my c is going to be plus 0, which obviously we don't need to write, and so just negative 9.8 t. And that's because velocity, the initial velocity was 0. So at this point, we had acceleration as negative 9.8, and now we have velocity as negative 9.8 t plus 0, or what I'm just going to write as negative 9.8 t. After velocity, we can find position, which is what I'm going to call h of t. H of t, of course, is going to be the integral of negative 9.8 t dt. The integral of negative 9.8 t. Add 1 to your power, divide by 2. So negative 9.8 divided by 2 t squared. And then, of course, plus c. Well, negative 9.8 divided by 2 is going to be negative 4.9 t squared plus c. Well, what do we know this time? And this time we know that h at 0 is 2,000. And so if h at 0 is 2,000, then this equation is going to be negative 4.9 t squared plus 2,000. So now we know that h of t is this negative 4.9 t squared plus 2,000. And again, of course, if you go based off of the generic form up above, we're matching up with negative 4.9 t squared plus v naught t plus h naught. So it asked me to do two things. Develop the position formula. So I'm going to say my position formula is h of t equals negative 4.9 t squared plus 2,000. The question also asked me to find how far above the Earth will the object be 20 seconds later. So we're finding how far above the Earth, we're trying to find the height at time t of 20. So we're trying to find, h of 20. I don't really have room to show the work there, but you know what to do. Plug in the 20 for t. So 20 squared is the 400 times the negative 4.9, and then add 2,000. And I have listed that you end up with 40. It's a height, so of course it is 40 meters. Okay. Officially, I showed myself developing it. We could have even showed a little bit more work of finding our c values, but again, since they were both values at time 0, it made it pretty easy to just plug the numbers on. Okay, example 2. A ball is thrown downward with a velocity of 40 meters per second from a height of 2,000 meters. Begin with the acceleration function and develop the position function for the ball. What will be the position of the ball after 8 seconds? So, if you notice, a similar problem to last time. If you identify some initial information, a ball is thrown downward with a velocity of 40 meters per second. What does that tell me? It's thrown downward with a velocity of 40 meters per second. So that means my initial velocity is going to be negative 40, if you would, because it was thrown downward. And then from a height of 2,000 meters. And so that is my initial height. Okay. Begin with acceleration. Well, A of t, we know acceleration. We're talking downward again, so negative 9.8. Nothing fancy there, nothing else to do, we just know the acceleration already. Okay, continuing along. From acceleration, we can find velocity. We find velocity by doing the integral. The integral of negative 9.8 dt, so the integral of acceleration, which the integral of negative 9.8 is negative 9.8 t plus c, of course. This time, our added information to help us find c is that v naught is negative 40. And so when you plug in, let me rewrite that. V naught, or v of 0, is negative 40. And so if you plug in 0 there, we will end up finding c to be negative 40. And so we end up with our equation being negative 9.8t. It's plus c, but c is negative 40, so minus 40. That is our velocity formula. From velocity, we can find the height or position, h of t. That, of course, is going to be the integral of negative 9.8t minus 40 dt. The integral of negative 9.8t, of course, add 1 to your power, divide by that new power of 2, ends up with negative 4.9 t squared minus the integral of 40 is 40t, and then officially plus c. However, this time, what do we know here? And for the initial height, we know that h of 0 was listed as 2,000. And so, plugging in 0 for t and saying that equal to 2,000, we would find that c is 2,000. So, gives us a position formula of negative 4.9 t squared minus 40t plus 2,000. And that is position. Okay, so what all did it ask me to do? Develop the position function. So, my position function, h of t equals negative 4.9 t squared minus 40t plus 2,000. And the other question was, what will be the position of the ball after 8 seconds? Position, again, is height. So we are looking for the height at time 8. So that would be taking our newly found height formula and plugging in 8. Again, I don't have the room. You guys have the calculators. Plug 8 into your formula, and I have written down that it should work out to be 1,366.4, and we are in meters. Okay, one more example here. Example 3. A boy stood on top of a building 40 meters high and threw a stone so that it had an initial velocity of 20 meters per second. Begin with the acceleration function and develop the velocity function and position function for the stone. How high will the stone go, and how long after the stone is thrown will it hit the ground? Okay, so if we identify what we're given, a boy stood on top of a building 40 meters high. So 40 meters high is going to be my initial height. So if you can see it there, I just wrote h naught. And threw a stone that had an initial velocity of 20 meters per second. Initial velocity of 20 meters per second is v naught. And I was just rereading. It doesn't say that he threw it downward, so it is a positive 20 this time. Okay, beginning with acceleration. Well, what do we know about acceleration? Our acceleration formula is going to be negative 9.8. In order to find velocity, we will integrate. So velocity is going to be the integral of negative 9.8 dt. Of course, the integral of negative 9.8 is negative 9.8 t plus c. In terms of velocity, since our velocity formula, we know that v of 0 is 20. So set it what you have equal to 20, put 0 in for t, and we find that c is 20. And so we have the equation negative 9.8t plus 20. And that is my velocity. From velocity, I can find height. So now we're going to integrate the integral of negative 9.8t plus 20 dt. The integral of negative 9.8t, negative 4.9 t squared, plus the integral of 20t plus c. This time we're working our height formula or equation, and we know that the initial height is 40. So h of 0 is 40, which means put in 0 for t, set the equation equal to 40, we will find c to be 40. And so negative 4.9 t squared plus 20t plus 40. And that is our height or position formula. So one of the things it did ask is to develop the position function. So one of my answers, h of t, is going to be the negative 4.9 t squared plus 20t plus 40. Okay, now we've got a few other questions to answer on this one. How high will the stone go? So right there, if we're being asked how high will the stone go, how do we figure that out? How high will the stone go? Well, how high will the stone go? When will it hit its peak? When what is 0? When the velocity is 0. So we developed a velocity formula along the way. We're going to set that equal to 0. And that is negative 9.8t plus 20 equals 0. I did not write 0 though, did I? There we go. Equals 0. Of course, subtract 20 over. Negative 9.8t equals negative 20. Negative 20 divided by negative 9.8. I have written down that it is 2.0408. And of course, all of this was meters per second, so that is going to be 2.0408 seconds. Now, is that our answer? That is the time when the velocity equals 0. So that is the time when the stone is its highest. But we want to know how high the stone will go. So how do we find the height of this stone? In order to find the height of the stone, you're going to have to take this time and put it into your height formula. So we're going to be finding h of 2.0408. Again, use your calculators. You're doing that 2.0408, plugging into the height formula you have right there. And I have written down that that is going to equal 60.4082. It is a height, so I'm going to label it in terms of meters. Okay, so right there, that answers how high will the stone go. And then we have one other question to answer, and that is how long after the stone is thrown will it hit the ground? I'm going to bring this one right over here. So how long after the stone is thrown will it hit the ground? Well, when the stone hits the ground, what do we know? And hopefully you're telling me that you know the height of the stone is 0. So we're going to use when h of t equals 0, which if you look at our h of t, it's negative 4.9 t squared plus 20t plus 40 equals 0. And how do we solve this equation for 0? Well, of course, we have that negative 4.9 out there. There is no nice, neat method here. We are using the quadratic formula. So, quadratic formula, if I set it up and at least write down the initial step, negative b, so negative 20, plus or minus the square root of b squared, so 20 squared, minus 4 times a, which is negative 4.9, times c, which is 40, all over 2a. So 2 times negative 4.9. As you can tell, I am out of space here. I trust that you can use your calculators. You can do quadratic formulas since you are now at calculus level. Plug that information into your calculator. Of course, we are going to get two answers. I have written down negative 1.4703, and I have written down 5.5520. And of course, we can't have two answers here. How long after the stone is thrown will it hit the ground? This is a time, which if this is a time, that means which one is our answer? And of course, we know the positive one is our answer. So it's going to be 5.5520, and this is a time, so I'm going to say seconds. Hopefully all of that shows up on the recording. I realize I'm kind of at the bottom of the screen, but I think I got it to work. Okay, that is lesson 65. I recorded this lesson early, so assuming we stay on track this week, that would mean that you are watching this on Friday, and so lesson 65 homework will be due on Monday. Have a great day.